obvious, being that it goes as 1 over r. But being that this is the same distance away from the charge, one would expect the potential to be the same. Equal potential lines are like contour lines of a map, which trace this line of equal altitude. You remember this, MGH. And so basically, in this case, the altitude, is the electric potential, our voltage. By the way, you guys are seeing the slides, right? I mean, what are you seeing?
Yeah, we're seeing a staircase.
Yeah, we can see it.
Yeah, we can see it. It's fine.
Okay.
Are you writing something on the slides or no?
What's that?
Are you writing something on the slides?
I am not.
Oh, okay.
Professor, could you go back to the last slide for a second?
Sure.
I just wanted to ask, this might be a silly question. What is K in this situation for the voltage of the point?
Oh, okay. This is this electric constant. It's 1 over 4 pi epsilon naught. Vacuum permeability. The number, I mean, in SI units is 9 times 10 to the 9th. I forget all the units.
Oh, okay. Yeah. Thank you.
Yeah. I mean, in reality, usually it's 8.99 times 10 to the 9th, but I don't know, it's just easy to remember. 9. you got 2 nines in that number. All right. Are you good? Okay.
Yes, thank you.
And if I can go to the next slide. Yeah, that's where we were. And again, I was just saying, the equal potential lines are always perpendicular to the electric field. And, in this case too, these contour lines are always perpendicular to the gravitational force, gravitational field, if you want to call it that. For instance, if you were to place a ball or something near the top or on the side, initially it would begin to fall perpendicular to these lines. Of course, what happens, when you build up momentum, then you have to contend with Newton's first law. I mean, you have momentum that will take you one way and the forces in the other way. So it's not going to, as it builds up speed, the dynamics is such that you would not have it being perpendicular all the way down. The centrifugal force and all that you would have to take into account. But if this was a mountain that was like a cone, perfectly shaped cone, then it would. I mean, because you would not have components that's tangential along these lines. It's just that's a special case. And I don't know if you guys can see me over here, but obviously, if you have you drop a ball and I don't know, you guys, can you see me over here?
We only see the slides.
Yeah, you're good.
Yeah, you have to go to his other screen.
The second camera in the chat.
It's the second camera.
Yeah,
You can double click on his video to maximize his video.
Now, does it switch over to me now? Okay. So, wow, see, here I go. Basically, if I drop a ball in a gravitational field, there's nothing impeding its direction. There's no constraints on the surface or anything. It just basically goes perpendicular to these, contour lines. It's straight down. I mean, you just think of these lines as like as GH. In the same sense, like the electric field, like a uniform electric field. But even in this situation here, I don't know whether you can see this, but it's a bowl, makes a half of a hemisphere.
Could you point the camera down a
Oh,
bit?
okay. Thank you. Can you see the bowl now?
Yes, thank you.
The best way to show this, but can you see these lines? They're like longitude lines running toward the center.
Yes.
Barely, but they are visible.
Yeah, they're there.
All right, yeah,
A little better.
that's better. Yeah.
Yeah.
Well, in this case, the longitudinal lines are perpendicular to the equal potential lines, like in a phi direction, if you think of it that way. And so, if I just release this metal ball without giving any push to it, it should follow the line all the way down. And this is a special case, this being that there won't be a tangential component. But you can see if I do this correctly, and I give it a push, it should just follow that longitude line back and forth. And basically, that's the point I'm getting at, is that, being that the line of force is always perpendicular, to these, constant potential surfaces, or constant potential lines, which in this case, you could call that like a constant height. Pretty cool if you had two of them. Two of them. And we'll start one a little different than the other. It's wide. You do that very well. This is more entertainment than anything else. All right. That's enough entertainment for today. We better move on. I just want to make that point that this motion is perpendicular to these equal potential lines, or contour lines, if you want to call them that. All right. So why are the equal potential lines perpendicular? I mean, we sort of described this qualitatively. I'll just kind of summarize that. So like we have this one case here where we have electric field here on the right. Okay, so it's off at some angle with respect to the path that we're taking through this electric field. And what is also shown is equal potential lines here, or surfaces. I guess if you want to project this into the page, but for most part, you can say these are just lines. And so as we move this charge through this path, basically, we're doing work. Being that theta is not 90 degrees. And if you want to do this in terms of potential, remember, this is to divide the force by the test charge, which is this Q naught. By doing so, that becomes the electric field, as opposed to the force divided by the test charge, same thing. And so now we have this this relationship of the change of potential is equal to the negative in this case. Since this is the electric field doing the work, not me. This is electric field doing the work, dotted into the path direction that we're taking. And so we can integrate over the path and get the total potential difference between, you can say like the initial and the final location of our path. Not necessarily infinity. I mean, that's what we were discussing yesterday. No guarantee at infinity this will be zero. So we don't know what this field is. In the case for a point charge, we're in good shape. But for a line charge, no, that does not work. So it's only for specific cases we can define zero. All right. So then we just have this relationship we've seen before multiple times. So if the displacement ds is perpendicular, right angles, to the electric field, the dot product, E dot ds equals zero. So the change of potential equals zero in that case. That is in the case where ds is perpendicular to the electric field. Such a path is taking, the potential does not change. And that the dot product is zero. So the path ds lies on an equal potential line. This is kind of the definition in this case. All right, so that being the case, if the path ds is parallel to the electric field, then ds must be perpendicular to the equal potential line. Basically, you can think of the electric field as the path of greatest change of the, it points in the path of greatest change of potential. So, up to this point, we have derived electric field potential, the electric potential, not electric field, electric potential with unknown electric field. And this is here. So we have a known electric field We have a path we take. And from that, we can determine the potential just based on the direction of our path. Now, electric field can be directly calculated. I mean, we can turn this argument around, and then you can say, well, the electric field can, in fact, be directly calculated from the electric potential by applying what is called the gradient operator. And this is probably likely your first introduction to vector calculus. Basically, what you're doing is you're converting a scalar field into a vector field. In this case, the scalar field is electric potential, and the vector field is electric field in this case. I don't know if you guys have seen partial derivatives.
We have. Well, for anyone here that's taken 243, I don't know if everyone has, but.
Yeah, I mean, I think some of us have.
Yeah, I mean, basically.
I'm taking it right now, and we haven't reached this part yet.
I mean, when you take a partial derivative with respect to x, for example, you ignore any dependencies on y and z. Those are just held constant. Even though y may depend on x or z may depend on x, you still just hold those quantities constant. And only those that part of the function that explicitly depends on x, so, that's what you take the derivative of. As opposed to like a regular derivative, I mean, you have to take into account of these dependencies, and the way you deal with that mathematically is something called a chain rule. That's the difference between these two. And this is a partial derivative with respect to x, for the in the I direction, in the x direction, partial respect to y in the y direction. And for the z direction, it's the partial respect to z. And this is denoted by this kind of upside down delta. The gradient of a scalar field is a vector field that points in the direction of greatest rate of increase or decrease of the scalar field. And of course, the magnitude is the rate of that increase. This is what's called, this is a gradient operator. And this type of operator can be used on a vector. You can dot this into a vector field, and that's usually referred to as the divergence. So, what is the tendency of that field to move away from a point? But that's getting beyond the scope of this course, actually. All right. So this just kind of gives you an idea of what a potential looks like. I mean, this is basically a contour. I mean, we showed earlier this for gravitation. And you can also do this as well for electric. I mean, this is basically just these lines that we saw earlier, except they're expanded out, into like into a height. And here what we have is 4 charges, 4-point charges of what it looks like. And one here, I don't know if you can see my mouse moving, in the sort of the, it's on the right. That's a positive charge, obviously, because you can see the potential gets higher and higher as you get close to the middle. And likewise, diagonally to that is a positive charge. Where on the top and bottom, those are negative. Now, if we could put like a fictitious type mass on this that has a charge, and you can see the path of the electric field. Let's see if I can get this to work. Oh, great. If you were to, okay, that's what I wanted to show. Yeah, this is basically the direction of the electric field. You can, I don't know if you can see these red arrows here, but that's basically the path of greatest descent. I don't know if I can get this. Oh, but this thing is not working. Sorry about that. Well, I'll put the link to this, but I don't know, it's actually good to visualize this in terms of releasing particles in this system. Maybe if I can bring up, Are you guys able to see this animation now?
No.
No.
We don't see an animation. We just see the slide.
Oh, okay.
and,
Let me.
and the link at the bottom.
Right. Let me stop